support team here at MSC, and today I'm going to be talking about multi-mass configurations with MASSSET, which is a new feature in MSC Nastran 2018. I'm just going to figure out how my button works here. Oh, there. Okay, so why are we talking about this? Well, in typical aerospace vehicle analysis, it requires the consideration of multi-mass cases involving different structural masses, payloads, fuel conditions, and environmental conditions. And previously, before this new feature was instituted, you had to handle these things with workarounds such as subcase-dependent MPCs and overlapping grids, etc. But now, with MMC, or otherwise known as MASSSET, that's been introduced in MSC Nastran 2018, you can specify mass increments using this MASSSET capability to construct additional mass configurations and conduct the analysis in a single run. So it's much easier. One thing to note is that mass cases are subcase selectable, similar to loads and boundary conditions. It's also almost analogous to adding an NSM, non-structural mass, which is also subcase selectable. The main difference here is that MASSSETs are structural masses. So in this presentation today, I'm going to basically cover how to use MASSSET through the case control, how to enter in the case control and bulk data entry. And then I'm going to do that by showing a sample case study using MASSSET and also a sample case study using MASSSET with part Superelement, which it supports. So here's a list of all the solutions that the MMC capability is supported. SOL 101, if you use a static analysis with initial relief, you can actually use a specified user-specified math case. In SOL 103, 107, and 110, you can calculate modes based on a user-specified math case. As you can see, we have virtually all the other solutions available in Nastran that supports MASSSET. So this is just something that I took straight out of the quick reference guide for MSC Nastran 2018. This is the case control entry for MASSSET, and as you can see, it's just like the load or SPC case control entry for load. I'm sorry, it's just like the entry for loads or SPCs for case control, where you actually, I'm sorry, for your model, where you basically just call it out in the case control, and it basically gets enabled, and call out an ID, which will be recalled again in the bulk data, and your MASSSET is enabled. The second component is the bulk data set, the bulk data card of MASSSET. And in this case, what the bulk data really is doing is it basically is defining a mass combination definition. So it's really, you're really putting down this equation here, which is basically a summation of all the incremental mass that you're actually going to be using for the model. I'm going to go through a little bit about this just in this slide, but I'm going to be covering a lot more in the subsequent slides and examples. So basically what you're doing is putting the MASSSET bulk data entry, and your ID will be basically the ID that you've already called out in your case control. And this first entry here is basically the overall scale factor that you're going to be multiplying your summation of your mass increments afterward. And everything else here is basically every one of your mass increments. The fourth field is basically your scale factor for the first mass increment. This is the scale factor for your second mass increment, and so on and so forth. Typically, when we're talking about mass increments, if you actually are going to be using a base mass, the first ID will be 0. And basically, I'm going to cover that in a couple of slides as well. But if your first ID is 0, that indicates the base mass. And I'm going to cover why, what difference is between base mass and other incremental mass. So here's a couple of rules and tips in using MMC capability. So there's really 3 components that you need to keep in mind when you're actually going to be enabling the MASSSET capability. The first is, again, the MASSSET case control. which selects a particular math case or combination to be used in the analysis at the subcase level. Okay, so basically you're calling this out in your subcase level. And the next thing that you have to keep in mind or enter is the MASSSET bulk data entry itself, which again defines the linear combination of math cases to form the subcase-dependent mass. And again, this is actually an important point. These entries should be defined in the main bulk. So if you will actually have different begins in your bulk data file, but it's important to actually include this math set or enter this math set card in the main bulk, not in the other bulk sections that's denoted by the other begins. So we talked about the first component, the second component, and the third component is basically the math increments themselves, which are defined using a separate begin statement and then followed by a math ID, which refers to basically the math ID that's referenced by the initial bulk data entry. So, I kind of misfired there. So basically here is the math ID of the base math, and here is the math ID of the first incremental math, which is basically the ID that we're calling out here on the begin statement. Okay. The label is optional, but if you actually type in the label here, it'll be recalled when you do when you look at your FO6, particularly when you do a param grid point request, and I'll talk about that a little bit later. Again, in the above math set example, there are two math conditions. As I said, this is basically the base math, which is denoted by the 0, and we've got a 1.0, always a real number or a scale factor that is going to be scaling this base mass, and then this scale factor, also a real number, is going to be scaling this mass increment. And this again is the overall scale factor for the summation of these mass increments. So using a particular math combination, it requires referencing the math combination's ID in MASSSET case control at the subcase level. And I've already kind of covered this, but an important point is if you're going to be using STAL 400, you do it at the step level. If you are going to define a MASSSET for a subcase, then you just basically leave that subcase without a MASSSET case control. In that case, what's going to happen is that you're going to be using the base mass for that subcase. So it's as if you're just doing a traditional non-MMC analysis. So here's an example of that. So subcase 101 here, as you can see, does not have a mass set called out. So hence, since there is no mass set case control here, only the base mass will be considered for this subcase. Subcase 102, on the other hand, does have a mass set set out. And that will be then using, the base mass and any incremental masses that I'm going to be defining using the bulk data and also the begin mass ID. Another couple of important points. This is something that bears repeating, but it's basically the MASSSET bulk data entry defines a linear combination of incremental base mass cases to form the subcase dependent mass. As I said before, the bulk data of the incremental mass is preceded by a begin statement, and then the word mass ID, and the ID that you called out in your MASSSET bulk data, where that ID is an integer. That's basically, it's going to be used for any mass increment case you're going to have. So the only data that will be used from the incremental mass bulk data section is the element connections and the element mass properties, including materials. So parameters and grid data included in the incremental mass section will be ignored. So in other words, you don't want to include any grid data in your incremental mass section because it just won't be even used. What it's actually going to be using is the grid data that's supplied in the base mass bulk data section, and then in the incremental mass section, the element properties is going to be used there. So in other words, you don't have to make a copy of your grid data for your incremental mass, but you do have to make a copy of your material, property, and element cards if you're, for example, changing the material. So again, I'm going to have an example of this if it's not clear right now. So typically, a user using MASSSET will construct an incremental mass by adding a concentrated mass such as ConM2 or CMass1, or by changing the material or element properties of the set of elements defined in the incremental mass bulk data section. And that's the example that I'm going to do right now. So here's a sample of the an MSC Nastran zip file. So here, this is a simple Sol 101, and as you can see, we have a subcase 1 that does not have a mass set defined, and we have a subcase 2 that does have a mass set case control defined. So we've actually specified a mass set case control with an ID of 12, and here we see that the case control again is the ID is then recalled in the mass set bulk data entry here. So here again is the mass set bulk data entry that basically is the equation that sums up together all the mass increments and multiplies it by this overall scale factor, and et cetera. So I'm going to go over a little bit more. I think I'm going to be repetitive, but it bears repetition here. So here is basically the first ID of the first mass increment, since we're actually specifying 0. This is the base mass condition. And here, this is the first mass increment, which I'm going to show you is in the next page, which you don't see right now. However, I do want to point out that basically we are specifying 0 here, and here's our begin bulk, where we actually do specify mass ID equals 0, which corresponds to this base mass. However, this is completely optional. You don't actually have to explicitly specify mass ID equals 0, because it's just assumed if you don't have a mass ID specified in your begin bulk, then that begin bulk denotes basically the base mass case or the 0 mass ID case. And again, this label is completely optional, but it's always nice to know what you're looking at when you're actually looking at your FO6 a little bit later. Notice that the begin bulk is in the main bulk data section, not in, I'm sorry, I take that back. The mass set is actually in the main bulk data section, not in the bulk data section that begins the mass increment, okay? That's something important to know. So again, this is just the model the model bulk data that describes the model itself. So what we're going to be changing here is basically the density for this model. We're going to change this field, which is density, to basically double the density, and that's doubling the mass. So what we're going to do is simply insert in the lower part of our BDF a begin statement with the mass ID that we called out earlier. This is the mass ID 101 that I called out earlier in my mass set bulk data card, optional label here, where I'm describing what it is. I'm basically doing a mass increment using a different material density. And as you notice here, I am basically repeating what is actually going to be needed for me to define this mass increment that has a different density for this iteration of my model. So basically I'm changing, or actually just doubling the density to 0.18 instead of 0.09. But notice that I'm actually including the property, which is again referenced by material, and also the one element in this case that is affected by this change. Notice that I did not include any of the nodes or any of the loads that were in my base mass set, okay? So again, the incremental mass will be computed based on the grid data that's supplied in the base mass bulk data section. So it's basically going to refer to the grids that have already been defined in the main bulk data section. And whatever that I have here, that is going to be the one that's actually being used for my incremental mass. So the element properties supplied an incremental mass section, which is repeated here for the different material density. So that's a simple example. So now we're going to just kind of talk about this a little bit, a little bit more complicated example called with actually like a C-quad and hex 8 solids. So what we're going to do here is we're going to use MASSSET and MAT1 to set up the following conditions, and then check the FO6 grid point weight output results for what we've just done. So basically, we have a base mass condition for this model, which has a volume and a density, and then we're going to do an incremental mass condition, which has the same volume but a different mass density for the material. Okay. And then we're actually going to do a mass combination set. We're actually going to take a look at the mass combination set that is actually the sum of the two masses that's going to be output in the FO6. So I'm going to switch over to the actual bulk data itself here just to show you the actual syntax of it. So I'm going to click on this. Can you see this? Maximize.
Yeah.
Is that better?
Yeah, that's
great. So this again is just the actual bulk data file for that model that I just showed you previously. And what we're seeing here is basically the subcase with first step that does not have a mass set defined, and we have a subcase 2 with the second step with a mass set defined here. Mass set 11 is what we're calling this this mass set in the case control. And here we have the mass set bulk data entry, which has the ID that we called out in the case control here, an overall scale factor of 1, for the base mass, which is 0, scale factor of 1 for the mass increment, which is denoted here by 101. So one thing to note that I'm going to show you here is that we're actually asking for the grid point weight generator output right here with param, GRD, PNT, 0, something that I suggest you also request. So what we're actually going to change here again is the material, just the material density. So we're going to scroll down here and take a look at the material that we have, MAT1. These two MAT1s will have a different mass density for my mass increment. So I'm going to scroll down further and kind of show you what's already been done in this PDF. So again, take notice that all the grids are in the main bulk data section, but as soon as I actually point out where the mass increment begin starts, this is basically where we start the mass increment, which is denoted by the ID 101. We do not have any of the grids repeated here. Only the P shell, the C quad for that P shell, the P solid for the C hexas and the C hexas themselves. And then if we scroll all the way down, we now see the two mass ones that have now been edited with a different mass density. Okay. So when we run this, what we get is an FO6 that, since we did request the param GRD PNT 0, which is going to write out the grid point weight generator output, we see that we do have that data here, and it'll actually give us the totals for the mass for our three different cases, and basically the base mass, the incremental mass, and the sum of the two. So here is the first one. This is basically the base mass, which doesn't really have a title because I didn't put one, okay? And then here is the incremental mass, where we change the density to that smaller value. And you can see that it actually says here, incremental mass ID, for mass ID 101, and here is the mass for that. And if we scroll down a little bit further, we'll see that there's an output from the grid point weight generator that says mass combination set for mass ID 11, which is basically the original mass ID, or the original ID we actually used for the mass set itself. So this mass here is basically a sum of the first two, okay? Again, not something that is too practical to use for our example, but it's just something that is actually what method is designed to actually output. Okay, so let me go back to my parse points. So what I've just what I've just demonstrated is basically outlined in words in the following slides so that it can be kept in for posterity in the documentation when we actually put this out there. So again, we see that the base mass condition, we don't have the MASSSET case control for subcase 1, but for subcase 2, we actually do call out the MASSSET case control. We request the output from the grid point weight generator. And in the begin bulk section, we actually have the MASSSET bulk data entry. And then for the base mass condition, we just have what it was before. We actually now specify the incremental mass condition with the ID that's called out from the main MASSSET bulk data entry. And we now, underneath the begin mass ID, we then change the materials density to reflect what we want to actually see. And if we actually do hand calcs, we verify that what we actually calculate using our hand calculations is the same as what we saw in the FO6 itself. So here's basically that what we just saw in the FO6 itself. And this is again the mass combination set for the two combined. So I'm going to do basically a kind of a live demo on another model. Basically what I'm going to be showing you is a very simple model, just a one element model with two nodes. And what we're going to do is we're going to add an incremental mass that uses, again, the same material but with a different density. And we're going to look at the base mass, incremental mass, and mass combination results so that we can answer this table here. What is the base mass condition, what is the incremental mass condition, and what is the mass combination of the two. So first thing I'm going to do is go back to my text editor. So here is my very simple beam model. So what I'm going to do here is, again, just kind of reiterate the concepts that I've talked about so far. I'm going to enter the mass set. So I'm going to put in my mass set ID of 111 here. And then in the begin bulk, I can then type in my MASSSET bulk data entry, referring back to the actual ID that I used for my case control there, 111. This is the real number that denotes the, again, overall scale factor for the entire linear combination of mass. This is my first, the scale factor for my first mass increment, which in this case is 0. The base mass, and then 1.0 is the real scale factor for my first mass increment, which I'll just, let's say, call it 101. You can call it anything you want, but I've been keeping these IDs as kind of the same, so I'm going to use 101. Now, the first thing I'm going to do is, again, I don't have to specify mass ID 0 here. That's really not necessary, but I can if I wanted to, so I will just leave that as is. And then the next thing I'm going to do is actually set my begin statement for my first mass increment. So I'm going to do begin mass ID. Another thing, mass ID in this case is only spelled with 2 S's, just a pointer. So I'm going to do mass ID 101. And then I'm going to copy over the P bar and T bar and MAT1 into this mass increment. And I'm going to change this to this value to the density field to 0.18. And then last but not least, I'm going to request my param DRD PNT 0, and that's it. And then I'm ready to run. So when I run this, what I'm going to get back is this FO6, which has, I called up the wrong one, I'm sorry. Hold on a second. So this is the solution for that. So if I scroll down, I'm going to have my my mass for the base mass and the incremental mass, which I've labeled in this case. I actually labeled incremental mass, and here's that result. And then if I scroll down further, here's the mass combination set for mass ID 111, which is basically again the summation of the two. So getting back to my PowerPoint. Oops. I'm adding the MASSSET case control to the subcase, the MASSSET bulk data entry, adding a new begin statement for the mass ID of the incremental mass. I did it also for the base mass, but again I said that's optional. Added the elements and element properties and material with a new density to the under the begin statement of the incremental mass. Added the param grid point 0 to invoke the grid point weight generator output, and I run it, and I look for the grid point weight generator output in the FO6, and therefore I'm able to complete the table. And as we saw before, we actually did see these values in the FO6. So again, this is just something that this is a summary of what I did here that will be included in the in this document, which will be archived with this video. So next, we're going to talk about using the MMC capability with part super elements. Now, this is the only super element that we actually support. We're not supporting external super elements yet for MASSSETs. So, but if you are going to be using MASSSETs with part super elements, the mass increments related to these super elements are also specified in a separate bulk data section. So here's an example. We have a begin super 2, which is basically, here indicates the super element 2 that we're specifying in the model. And, you know, here's the mass ID, we've seen this before, the optional label. So here's basically an example that we're going to kind of go through just to illustrate what, how it kind of works for part super elements. Here we have a part super element model that, that at first does not have a CONM2 attached to it. So it's basically just a series of 10 quad elements split out in this way to separate super elements, and it's residual. So this is the base mass condition, and the incremental mass condition with CONM2 is basically going to get CONM2 on node 3 on the super element 2 here, and a CONM2 on super element 0 is the residual on node 6, as seen here. So for the sake of clarity, what I'm doing here is actually I'm breaking out each of these super elements and the residual models into its own BDS, and I'm going to provide all of these files in a zip so that it's going to be included in the archive of this presentation. One thing to note is that I'm actually putting my param grid point request in each one of these stub files. Okay. You can view either this or enter the param grid point request in the case control. You cannot, however, put it in the main bulk data section as you're probably normally doing, because these are the rules of part super element when it comes to params. Okay, so that's one thing to note in this. So here we actually take a look at the master BDF, where we actually do call out my sub BDS for my super elements and residual. This is a simple modal analysis, and as you can see, we've actually have already. I'm sorry, misfired there. Here's our MASSSET. So we are going to be using MASSSETs here. So first thing we're going to kind of point out is that in the residual structure with the base mass, there's two residual structures. There's one with the base mass and one without. So here, this is the one with the base mass, and all we're doing here is including the breakout submodel, which I'm actually color coding just for clarity's sake. And here in the main bulk data section, we actually have the MASSSET, which is basically that equation that determines the linear combination. So Next, what we're doing is the residual structure with the CONM2 master increment itself. And here, we're just adding the CONM2 directly into it. We're not really, in this case, we're not really repeating anything because we're just adding a CONM2 to the base structure. So here, basically, is the ID of the CONM2, the node at which it's applied, and the mass of the CONM2 itself. And here, we actually have the begin mass ID of 101, which is basically this, that refers to this. And again, this one is the base mass, which is basically refers to the base mass of the residual. And then 102 is something that we'll see in the next page, okay? Now, before we actually get to that, we do have a superelement 1, which we notice does not have any CONM2 attached to it, so therefore it's just going to be base mass alone. And so therefore, that's all it is. So we have the begin super 1, and then we actually have the include for that submodel, but that's it. So if you turn the page, now we're actually dealing with superelement 2. Again, superelement 2 has a base mass and an incremental mass. So here's the base mass, where we actually do begin super 2 without anything. But when we actually do the incremental mass, we call out the 102, which is something that we called out before in the mass set bulk data. And here, we're actually applying the CONM2 to node 3 with that mass. So when we run this, what we'll actually get in the FO6, since we did request a prime grid point output, is this result. So I've actually kind of sanitized it in this table. But basically, what we're going to be seeing is that superelement 1, which does not have a mass increment, it's just basically the mass of that model itself. Superelement 2, which has the base mass, which has the base mass and a mass increment, will actually output these two masses. And here is where it actually, where the linear combination really comes into play. The mass combination actually does give you the sum of the two. And in our residual structure, same thing happens. So we actually do have the sum of the two, basically the base mass and mass increment together gives us the mass combination in this case. So just for fun, we actually did a baseline model with no mass sets and no superelements, and compared it to our model that uses superelements and mass sets, and we compared the model results, and they do correlate. So basically, you know, it's something that you can use for superelements as long as it's a part superelement. And that actually concludes my presentation. Let's open it up for questions.